much. I'd like to thank the organizer for giving me this opportunity of the talk. So I'd like to continue to talk about our work in progress and this is in collaboration with AU and also students, Chen in NTU and also my students, Nodomu, in our group. So basically, Hei already gave a nice talk about the gravity curve of the Euclidean object clock, basically. And but now in my talk, I'd like to more focus on Lorentzian aspects of the same topic. So recently, there are renewed interest on Lorentzian CFT because there are many developments based on triggered by conformal bootstrap program. So the few of the nice applications includes a analytic bootstrap. So here you basically consider the light-form limit of the conformal block to get some bounds on the structure of CFT. And also there appears nice interesting formula, so-called Lorentzian inversion formula. So you can read out the OT coefficient from the Lorentzian 4-point function. So by using kind of invert the 4-point function using a kind of weird conformal block. Okay? So and also there are some applications on the light-form OP. So you can derive so-called ANEC, so this is aberration nullities condition, so which is very important. And important assumption to derive so-called Hoffman-Martian bound about 10 years ago. But this can be derived on the block space using some orderly constraint and also using the positivity of the OPE. And so there are many interests on Lorentzian CFT. So I hope to revisit the OP structure of the Lorentzian CFT, and I want to derive some a colloquial description of the block. Yeah. Okay. So here is the outline. So I'd like to review on Lorentzian CFT briefly, and I then move to the derivation of the Lorentzian OP block. Now, in Henyu's talk, so he used a so-called shadow projector in position space. But now, in the Lorentzian case, it's actually useful to use a momentum space shadow projector. So I briefly explain it in my talk. And now, then I proceed to consider the gravitational dual of the Lorentzian OP block. So there are two cases. Okay, in Lorentzian signature, you have causal structure. So one is a space-like, and the other is time-like. And the space-like case is very similar to the Euclidean case. And you talked about. Actually, so inside the OP block, so so-called the HKL field naturally arises. And the HKL field lives on AD space in one higher dimensions. But if you consider the time-like case, you can also find some interesting field, so which is similar to the HKL and LL. But this field is not on the ADS, but on what we call hyperboloid. So this one is different from ADS space. So this is a new findings in our work, and I will summarize. Okay, so in Lorentzian CFT, so basically, so why do we care about Lorentzian CFT? So basically, Lorentzian CFT can be constructed from Euclidean CFT. So you don't have to consider Lorentzian CFT from the scratch. But so there is a nice theorem by Lucian, and also there are nice theorems, so also the Schroeder theorem, to reconstruct the Lorentzian theory from Euclidean. So basically, you just use the Einstein prescription to construct variation function in Lorentzian CFT. It's fine because you are guaranteed to get a correct Lorentzian theory from Euclidean. But now there are slight difference between Euclidean and Lorentzian. Basically Lorentzian CFT can be defined by the following data. This is mostly the same as the Euclidean case. So you are given a set of primary operators, so OI. So this is a irreducible representation of the conformal group in Lorentzian signature. So you have SO2 comma D. So previously, so in Euclidean signature, so you have SO1 comma D plus 1. So there are a slight difference. So the primary operators are labeled by delta J and lambda. So delta corresponds to the conformal dimension. And J, this is supposed to be spin, but now, so J is a representation in SO1, so J can be continuous in this case. So previously, delta is also in the representation in the label for SO1, so delta is of course naturally continuous. But now, in Lorentzian case, the spin can be continuous as well. Even if you are focused on unitary representation, so then J can be continuous. So that's a new feature. And lambda is the representation for the rotational group, but I only focus on the scalar part, the trivial representation for lambda in my talk. Okay. So CFT can be defined by giving a set of primary operators, and also you need to give the OP coefficients between the primaries. So if you have a OPs, then its structure, okay, the OP basically can be completely fixed by conformal symmetry up to one constant, C, I, J, K. So I, J are some representation labeling primaries. And now on the right hand side, you have primary part, and then you have some power, so which can be completely fixed by conformal dimensions. But now you have a lot of descendant terms. So basically, these are derivatives of the primaries. But this part can be completely fixed by conformal symmetry only. So so basically, so to label these a representation, okay, now I'm going to focus on the trivial representation for lambda. So now the representation, primaries are labeled by delta and Z only, and they have quadratic Casimir, so given by this. Okay, and now, so in Euclidean case, if you are familiar with so-called shadow formalism, then maybe you already noticed that, okay, here, so you can exchange the roles of delta and delta minus t. So even if you switch the role of delta and t minus delta, so this part is invariant. But in Lorentzian signature, so there are additional symmetries. So one of them is so-called spin shadow transform. So can you explain it in this talk already? So this is the spin shadow transform. So you just change the J, replace J with 2 minus D minus J. But then, so the quadratic Casimir still doesn't change. Okay, so you have symmetry exchanging J to 2 minus D minus J. And also, there are more exotic transformations. The one of them is so-called light transform. So you replace delta with 1 minus J and J with 1 minus delta. Even if you do this, quadratic Casimir doesn't change. So in Lorentzian case, so you have more symmetries than the Euclidean case. And so these transformations forms so-called restricted line group of order A. So this is a dihedral group SO2 comma D, satisfying these relations. And now, so you can construct a familiar shadow transform from L and Sj like this. And there are more transformations you can construct. Okay, so there are many symmetries in Lorentzian series. So now let me go back to the OP structure. So in CFT, OP is convergent on the CFT vacuum, so which is proved by Matt about 40 years ago. So basically, so the OP, okay, if you have OP of OI and OJ, then you can decompose it into the irreducible representations on the right hand side. So K labels the irreducible representations. So the right hand side is a bivocal function, so x1, x2, and labeled by ijk. And this block, okay, so this is now, okay, in all days, I don't know how they call it, but recently so it is called the OP block. Okay. So this is the OP block, and which appears in different places recently. So for instance, if you consider the perturbation of the entanglement entropy, then so such an OP block naturally appears. And okay, so there are another cases you see you find the OP block. So you can completely fix the structure of the OP block just by using conformal invariance, and which was completely done in 70s. But now, so I'd like to give a live derivation of the OP block. So using shadow projector. So in Euclidean case, so what shadow projector tells us is that you have some different function of the identity. Okay, so you have some projector. So this is a projector to reducible representation labeled by K, and you sum over K, then you can construct the identity. It's very similar to the quantum mechanics. And this projector is constructed by using so-called shadow operator, O tilde. And here, O tilde transforms in the representation, so K bar. So K bar has a different conformal dimension. So this is the shadow field with dimension E minus delta K. And you just prepare the kept states for the shadow and then bracket for the origin operator. So this is supposed to be a projector in Euclidean signature, and if you naively use this in Lorentzian case, you would end up with some integral representation of Bijk. Okay. Here, so I just insert one into the both sides of them. Okay. So you just insert one here, and use this definition, and then you end up with the 3-point function on y or j and O tilde k minus OK. Okay, so this is an integral representation of the opical, and it is correct in Euclidean signature. But as Henry already pointed out, so it's not clear what kind of 3-point function you have here. So because in Lorentzian case, so there are several types of 3-point functions. So Feynman or time order. Okay, so in this derivation, it's not clear. So what's the correct 3-point function you should use here? And also, it's not also clear whether this projector is complete in Lorentzian. Yes.
Actually, that's one question. Whether the
completeness.
Yeah, completeness.
Yeah. So okay, I will talk about this in a couple of slides. In Euclidean case, actually, so this is over complete because you have shadow configuration. Yes. Okay. But in Lorentzian case, you can, if you use the so-called momentum shadow projector, which I'm going to tell you, then you can construct a complete projector. Okay, so now, instead of using the position space picture, let me use so-called momentum space shadow converter. So this is developed recently by Rios and his collaborators. This is pretty nice because, in momentum space, the causality is very clear, and causality, you can easily maintain the causality and also unitarity. So here, so instead of having the position space projector, now you construct a momentum space projector using the Fourier transform states. Okay, so this is just the states created by acting OK on the states. Okay. And this state is a also normal basis with positive limit inner product. So this is nothing but the Whiteman 2-point function, okay? Because you just put these operators on in this order. This is just a Whiteman function. So these are this state is normal in this way, and it is manifest that the trivial space is positive limit. So so this is a complete eigenbasis. And in momentum space, the shadow field is now defined by just multiplying the 2-point function on all k. So this is how you construct the momentum space shadow. So now I'm going to use this projector to construct the OP block. Now, if you then just apply the momentum space shadow, then so you will end up with this form. So here we have a 3-point function, Wij. This is actually just Whiteman 3-point function in the given ordering. But now the third operator is now Fourier transform. It is in the momentum space representation. And you multiply W, so 3-point function, because you are supposed to have O tilde here. So O tilde is defined by this. So you end up with this form. Basically, so this Whiteman 3-point function can be constructed just by using an analytic continuation from the Euclidean correlator. So I guess most of you are familiar with this resolution, so I won't explain it in detail. But anyway, so you can easily construct the three-point function, and you make a Fourier transformation for the start point. And everything has been done in all days in 70s by these gentlemen, so legendary paper. And in the Lorentzian case, so there are two distinct cases, and one is space-like and time-like cases. And so space-like cases has been also actually considered, in 70s, and there are tons of literature. So okay, now I'm going to focus on the space-like case, and also I focus on the scalar OPE, so O1 and O2. These are just scalar operators. And in this case, on the right-hand side, you only have spin J contribution due to the symmetry restriction. So on the right-hand side, you have spin J OP block. And I also focus on the scalar block for simplicity. So you can actually compute, you can rewrite the OP block in this case using the previous formula. And I won't show you any detail about that. Okay, I just give you outline how to rewrite this guy. Okay, so you basically rewrite the three-point function by introducing Schwinger or Feynman parameters. Actually, this is exactly equal to equivalent to what you did in this part. So you just rewrite the three-point function and by introducing Schwinger parameter. And after some math, and then so you perform the Fourier transformation to go back to the position space. Because the project was written in the momentum space. So I just give you the result. Okay, for the scalar primary, so when J is equal to 0, so when you find a something like this, so here, so you have some bulk, so-called bulk field phi L, and multiplied by some factor of U here. Okay, this is actually equal to what you showed us in this talk after the definition of U. Okay, so but before that, let me explain the role of these parameters. So here I introduced two parameters, two types of parameters. So x mu of U is just interpolate 2 points, okay, x1 and x2. So you run from 0 to 1. So when U is 0, you are at x2. But when U goes to 1, then you are at x1. This is, okay, x mu of U interpolate between x1 and x2. Okay. Now, so you can also introduce another parameter, eta. So this can be interpreted as a holographic coordinate in ABS, in quantum touch. And actually, so U is a geodesic parameter. So okay, so this is actually on the geodesic in ABS space. And also the field I defined here is nothing but so-called HK area field of an ABS scalar. So whose form is given here. Okay, so basically you have some propagator from boundary to bulk, but in Lorentzian signature, so you need to have some weak rotation. So you first prepare your state in Lorentzian signature and connect to the Lorentzian signature. So this is what HK representation tells us. Okay, anyway, so this is the expression for the HKL. So this, okay, originally HKL derived this representation by just solving the equation motion in ADS space. But now here, so we don't use any equation motion in ADS. We just rewrite the OP code, and we end up with the same result. Okay. So this is curious. And as a consistency check, okay, so this field is supposed to be a solution of the equation motion in the bulk space. But the equation motion actually follows from the Guadalini-Kashmir equation for the OP law. And if you identify mass squared with this value, so this is the canonical identification in ABCP. So the Guadalini-Kashmir equation turns out to be equal to the equation motion, and this structure actually applies to higher speed cases as well. Okay, and also after changing the variable, so you from lambda then, so this representation matches a Euclidean result in use form. Okay, up to the difference of the signature.
Therefore, these results of finding general safety is not necessarily related.
Yeah, this is general. Yeah.
I don't
take. I don't take any larger limit. Yeah. No,
Still, you see somehow AD is metric and general.
Right.
Do you have a good interpretation of that?
Well, basically everything is fixed by conformal symmetry. So we only have a we only look at the kinematical part.
Yes, it's probably more broader than just AD.
Yeah. So okay, yeah, that's a good question. So if you have a real ADS gravity law, then so you need to take a larger limit. Such information should be included in the OP coefficient. Yeah. But now we only look at the kinematical part of the structure. So yeah, that's why it works so well. Okay, so in the last couple of minutes, so let me talk about the timeline case. Basically, in the timeline case can be also treated in the similar way to the space one case. But now, so x12 squared is now negative. So in the spatial case, x12 squared is positive, but now it is negative. So you need to analytically continue x12 squared appropriately. But it is actually not so difficult to do that. And after doing the analytic continuation, so you end up with a very similar form as before, but with slight difference. So previously, so we defined coordinate incorporating x1, x2. Okay, this doesn't change. But previously we defined eta w here. So this can be negative. x1 to squared becomes negative, then eta becomes imaginary. So you need to redefine the correct coordinate. So now we go chi of u. So now we have absolute value to make it real. So interestingly, so now, so once you define these coordinates, then so this can be regarded as a geodesic, not on the edge space, but on the hyperboloid, so in R3, 2. Okay. So now you have two type of directions. So this hyperboloid, it can be given a metric of this type. So this looks the same as Rosetta space, but now we have analytic continuation in the time, okay, in the Euclidean time direction here at each constant time. Okay, so this is kind of weird, but such a parameterization naturally arises in the timeline case. So this is, yeah, we think it is very interesting to look into more carefully. This is what we did. Okay, so this is the story in the timeline case. So okay, and also we can also define a scalar field living on the hyperboloid, and you can actually write say the HKL type formula to represent a scalar field propagating on the hyperboloid. Okay, so this is almost the same as HKL formula, but the way of the analytic continuation is slightly different. So previously, we analytically continue the spatial direction, but now we have big rotation for time. So this is a kind of picture illustrating the HKL construction and its counterpart in timeline case. So in the HKL representation, so okay, this is my Lorentzian Minkowski slice, and this is AD space in Lorentzian signature. So eta is the progress coordinate. So okay, to construct a bulk field, bulk scalar field, so you first prepare a state in Euclidean signature. Okay, this is the Euclidean space, okay, RD. And you first prepare your state on this slice, and you propagate this state using HKL kernel to the Lorentzian signature. So this is a picture of the HKL. Now, so we have a hyperboloid, okay, and so this is the Minkowski space, R1, -1, and now you prepare your state on the Euclidean section, the Euclidean space, and you let it propagate to the bulk using this coordinate. So this is what we found. Okay. Okay, let me summarize. Okay, so basically, so we derived a holographic representation of Lorentzian OP blocks So in the space-like case, we end up with the same formula as the HKRL. And but in the time-like case, so we find kind of interesting representation of a curved field living on the hyperbole. So this is kind of new. And our story can be easily generalized to the higher spin fields in the equilibrium case. And yeah, even in the Lorentzian symmetry. And but there are a kind of future problem. And so okay, there is actually another proposal for the timelike OP block. So this is proposed by about the second collaborators and also the lower collaborators a few years ago. So they argue that okay, without any derivation, but they based on some consistency. So they argue that the timelike OP block can be calculated by using so-called Sharp-Witten diagram. So Sharp-Witten diagram is kind of curious. So here, so okay, this is so-called the causal diamond between timelike separated point x1, x2. So we have causal diamond, and if you have causal diamond, then so you can naturally associate a codimension to surface in the space-like section, and you draw some kind of RT surface, RT-like surface in the ball, and you smear the sphere field on it, and then you can get the timelike OP block. So this is their proposal. Unfortunately, so we couldn't reproduce their proposal in our formalism. So we end up with a slightly different prescription. So it would be interesting to reproduce their proposal using our techniques. Okay, thank you very much.
Yeah, I have two questions. First, so for this one. At some point, are you using the momentum space version of the HKL? That point of view, it's more like a smear over the whole space, not like a subdivision.
No.
So
Yeah, in momentum space, you have restrictions.
yeah, in the momentum space, but here, if you translate into the coordinate, it sounds like there is no subregion in the coordinates. If you smear over the momentum space, so.
I'd say okay. So using this momentum space shadow, then naturally encodes the causality.
Yes. Yes.
Yeah.
But does it consider with this subregion where this Yantugo and the people did?
Oh yeah, that's a very good question. Okay, actually we try to resolve it. Yeah. In our paper, right? Yeah. So in their paper, okay. So I just only explain the Sharp-Witten prescription, but they also proposed a timelike OP block in theory instead of time. So they argue that the timelike OP block can be given just smearing the shadow field inside the causal diamond. Actually, yeah, we can reproduce it from our prediction.
And the second question is, you can consider like a conformal, like some generator acting on this left hand side by local operator, and then you push into the on the right hand side that can be pushed into the through this corner. Then you can check that whether it acts on the how it acts on the bulk field. So
Sorry, could you repeat your question?
I mean, you can consider this conformal generator acting on the left hand side,
Yeah.
to both sides,
Yes.
and then that acts on your corner, and then you can already change, and then you can see how it acts on the bulk field, and then does it correspond to the conformal symmetry in that case, or like
Yes.
isometry?
Yes. You can intertwine the action on both sides.
And in fact, like that's a strategy we're going to use to compute the correlation function later on.
Right. So actually, so to derive the Casimir equation, so you can add the Casimir equation, quantum Casimir, to the OP block. Then, so basically, so the Casimir operator acts on the 3-point function inside the kernel. Then the action, the Casimir acts on x1, x2, but it can be replaced with action on the third point. Then you get.
But that is from the point of the CFT, still CFT, but you define some
It's
bulk
also
field
possible.
using introducing extra field.
I think that's what to do and it's probably the speed in the future.
Any more questions?
Just a quick one. So since you're mentioning that you're going to use this to compute a 4-point correlator later on, and so these 4-point correlators in Lorentzian signature, you have these light singularities with the operators, and Wong's been arguing that these are related to 12-point singularity. So I'm not very familiar with that, but does this naturally just does the residues of those 12-point singularities in this light region are just simply related to your 3-point blocks? Or you see this kind of singularity structure more?
We haven't thought about say like case so far. So we only consider space and case and also time case. So if you consider light homology, for instance, then there should be some singularity.
Yes.
Yes. Yeah, that would be very interesting.
No more questions. Let's thank the speaker again.
We have done outside. So I would like to ask people who have been involved in the organization of this meeting and anyone who is interested to organize involved in organization in the future, or if you have any comments, then we will get here to just have that chat over things.